Can you see my screen?
Yes.
Yeah.
Okay, so
Can you make it?
can you hear me well? Can you hear me fine?
Yeah, yeah.
Yes.
Okay, so Stefano will read it from here.
We had a problem with the microphone. Probably doesn't work very good. Okay, we start again. So I was saying we dealt with qualitative temporal reasoning, which is a starting point also for quantitative systems. So the tractable fragments are interesting in both cases. We saw the interval algebra and the point algebra in the linear case. In particular, for the interval algebra, we have 13 basic relations, which everybody knows here are depicted in this figure. We have operations. The most used operations are converse, intersection, weak composition, and strong composition. Now, weak composition and strong composition sometimes are not explicitly separated, but in our work we make this distinction, which we think it's important to make. We call subalgebras the sets which are closed under all of these operations. We make instances which are pairs of events and relations which we want to solve in some way. We will see how later. We mean by an interpretation, a realization of the instance, or an assignment of basic relations to each relation in the instance, and a model is a valid interpretation. We embed them as labeled digraphs, which is the standard way to embed such instances. The problems we usually deal with are consistency and minimality. Since the two problems are equivalent under polynomial Turing reduction, we focused only on consistency, so we did not deal with minimality, which from the tractability perspective is the same. We say that a fragment is tractable if its consistency problem is tractable, and a fragment is tractable if and only if its closure is tractable. So we take a fragment, we generate the least subalgebra, and if the subalgebra is tractable, the fragment is tractable, and vice versa. So we are only interested usually in maximal tractable subalgebras because normal fragments don't have nice properties and the tractability follows. In the history of linear tractability, we have some milestones we decided to highlight. The fact that the path consistency algorithm is a key element of tractability. Many fragments have been discovered based on the tractability by path consistency or some variation of the algorithm. In particular, one of the most used fragments is the Horn fragment, which is the only maximal tractable fragment of the linear algebra, which is tractable by path consistency. Sometimes, though, we have to deal with choices or alternatives which the standard linear algebra cannot express. So we need an extension of our model, a branching model, which accounts for the possibility that something may not even happen. So we have the branching point algebra and the branching interval algebra. In particularly the branching interval algebra uses trees as models for the branching time. So we don't have a complete partial order, but only a future branching model. We have 6 new relations, which are depicted in this figure, which add up to the 13 standard relations, basic relations of the interval algebra. In this example, we can see right after school, Bob and his friends will meet at the nearby restaurant. They decide whether to go to the cinema or to the theater, in which case they'll take the subway. So we can see that this particular model, this particular instance, sorry, which can happen in the reality, is not representable by a linear algebra. We need some branching relations to represent what could happen and what could not happen, like going to the cinema or to the theater. The results in the branching algebra, which is quite new, I think it originates in 2000s, in the early 2000s. Up to a couple years ago, there were not many fragments known to be tractable, except for the set of the basic relations. 2 years ago, the convex fragment was discovered, but it's quite small fragment, and it's not a real subalgebra in the sense that it's a weak subalgebra. It's closed under the strong composition operation, but it does not contain the undefined relation. So it has some nice properties, but it's not all that good. So we had several open questions to tackle, and we tried to, starting from results in the linear case, to get new results in the branching case. So we tried to simulate the interval, the Horn fragment of the interval algebra from the work of Nebel and Buchert. We devised a new ontology called T-ord, which is a pre-theory for 3 orders, whose actions are only Horn clauses. So any proposition, any Horn proposition in the theory can be solved by any polynomial algorithm which can solve Horn clauses, which can find satisfiable models for Horn clauses. Being a pre-theory, this means that it's not all of the valid T-ord propositions are valid branching tree models. But if we limit ourselves to a small set, we restrict the set of allowed relations to the positive relations and the not equals relations, which we can show through our representation theorem that indeed the T-ord theory is equivalent, is isomorphic to a 3 order. And here in the slide you can see an example of a valid T-ord proposition which is not representable on a 3 order, but which uses non-T-ord allowed relations like not before. And a valid T-ord Horn formula. So now we can define very simply the VA Horn fragment, the Horn fragment of the branching algebra, as the set of branching relations which can be translated into equivalent, explicit, and close minimal T-ord Horn formula through a mapping operator. Now, the T-ord theory talks about points, not intervals, so we need an intermediate step, which is polynomial. But we can see that the mapping is polynomial, solving Horn instances is polynomial, so the fragment we get is tractable indeed. We have a theorem which proves that path consistency is complete for our fragment, since we can show it will be equivalent to positive unitary solution, which, since it's complete for Horn theories, we can show that it's actually equivalent to path consistency in our case. So the Horn fragment is quite big. It's like 50 times more than the convex fragment, 4,500 relations, about 1% of the full branching algebra. It is a proper superset of both the Horn fragment of the linear algebra and the convex fragment of the branching algebra. It is maximal. It's a new result. It's not in this paper, but we have already submitted it to another conference. But there are some differences, some key differences from with the linear fragment. For example, the branching fragment, the branching Horn fragment does not contain all the pointizable relations, which was the case in the linear algebra. And it is not the only maximal subalgebra extending the set of the basic relations. So this is also a new result. We found a different, uncomparable fragment, which extends the basic relations and which is not the theorem fragment, while in the linear algebra, the theorem fragment was actually the same. We can use it in a typical branch and bound algorithm, like the ones shown by Michael before. Our algorithm works only with path consistency tractable subalgebras. With bigger fragments, we clearly get smaller branching factors. Our experiment shows, indeed, an improvement, and especially in some corner cases, which are the big differences which make the result so smaller. So this is all. There are still several open questions. If it is the only maximal subalgebra, and what are the exact boundaries of tractability in the branching algebra? Thank you for your attention. All the code used for the results is available publicly in this link. If you have any questions, I'm available. I will try to answer them.
Thank you, Stefano. We are open for questions.
I mean, I could ask, not ask, but continue.
Go ahead.
From the previous question. Essentially, if I take a look into your paper, you have algorithm 1, which is a backtracking algorithm, and you could apply this sort of local model based selection on lines 9 to 10. When you do the splitting and you try to choose about different possibilities, perhaps it would be better to choose a possibility that retains most of the local models there, and perhaps this could enhance your reasoner.
Yeah, in fact, the results were, as you can see from this chart, is not so much better than there are corner cases which make the usage of this fragment like 50 times faster than but it's corner cases. Yeah, the algorithm was not our main priority, so we used a quite simple one. Yeah. Our priority was to find the tractable fragment in itself. Yeah, but there is room for improvement, certainly.
Yes.
Any more questions? We can line up the third presentation by Alexander Bolotov.
Perfect.
You have the floor.